We're going to solve paper 4, May-June 2024. Let's get started. So the first question says that a long tube contains oil. A small ball is held at rest at the surface of the oil. At time t equals 0, the ball is released and begins to fall vertically through the oil. The question is define acceleration. As we know, acceleration is if you want, you can also add the formula. Acceleration is delta v divided by delta t, which basically means how velocity changes with time. The mass of the ball is 0.0075 kg, and calculate the resultant force acting on the ball when its acceleration is 2.8 meter per second. We know the formula for resultant force is F equals to ma, which would mean 0.0075 kg multiplied by 2.8 meter per second square. This equals to 0.021 Newton. Don't forget to write the units, it's extremely important. Question C, 1C. As the ball falls, speed v is recorded. Speed time graph is shown. Describe what happens between t equals 0 to t is 0.04 and explain why this happens. Now, what is the relationship between velocity and time? Now we know the gradient of velocity times graph is acceleration. In case you don't remember, you can know that gradient is change in y over change in x. Change in y would be delta v and change in x will be delta t. This is our acceleration. So if we find the gradient, we can know about the acceleration. Now, in this question, it's important to know the difference between describe and explain. When they say describe, we have to show what's happening in the graph, okay? Explain means to give reasons as to why those changes are happening. Between t is 0 and t equals 0.04, we basically have a slope that's becoming less and less steep all the way until it becomes flat. So we can say that acceleration decreases all the way until it reaches 0. Until it reaches 0. That happens around at 0.03 seconds. So here we get 2 points for describing. Explain why this happened. Initially, at time t equals 0, the object may only have it will have most of it is acceleration and small resistive force maybe. After some time, the resistive force is increasing while the acceleration remains same. So what happens is that resistive forces is increasing. This is the opposing force. And the resultant force, which is the difference between both of them, is becoming 0. Force decreases until it becomes 0 at 0.03 second. Now this velocity, when resultant force is 0, is known as terminal velocity. And the ball reaches terminal velocity. By drawing a tangent on figure 1.2, determine a value for the acceleration of the ball at t is 0.01 second. Alright, let's get rid of this. At t equal 0.01 second, we're supposed to draw our graph, a line here, a tangent here. Tangent. And then we can find our radius. Let's get 2 points. We can get this point and this point. So our points are 0 and 0.02, x1, y1. The second point is this, which would be 0.025, and the y point is 0.06. Acceleration is gradient, which is delta y over delta x, y2 minus y1. Divided by 0.025 minus 0. Figure shows two identical trolleys P and Q held on a frictionless horizontal surface. A load is fixed to trolley P. This is trolley P. This is trolley Q. The load is 1.5 kg. There is a compressed spring between trolley P and Q. The trolleys are released. As the spring expands, it pushes the trolleys apart. These springs are released, and the trolleys are pushed apart. Trolley Q moves to the right at a constant speed of 0.36 meter per second. The mass of each trolley is 1.2 kg. The mass of the load on the trolley is 1.5 kg. The spring has negligible mass. Calculate the speed at which trolley P moves to the left. We need to find this speed. So now what's happening here is that there is conservation of momentum. In a closed system, momentum before and after collision is equal unless there is an external force which is applied. Momentum m1v1 equals to m2v2. What is m1? 1.5 plus 1.2, because we have two loads, weight of the load and weight of our trolley, multiplied by v1. This is what we need to find, equals to m2, 1.2 into 0.36 equals to 0.16 meter per second. The kinetic energy of trolley Q when it moves at 0.36 meter per second. Now remember, kinetic energy equals to half mv squared. Half into mass is 1.2. This is the mass of our trolley, times 0.36. A very simple question, straightforward answer. 0.078. Again, joules unit is extremely important. State the energy transfer that takes place as the spring expands. So at first, the compressed spring has elastic energy. As the spring expands, the stored elastic energy is converted into kinetic energy of the trolley. Question number 3. Show the small block of ice floating in the beaker of warm water. State one way in which the motion of particles in ice differs from the motion of particles in water. Ice is a solid, water is a liquid. So we know that ice particles vibrate in fixed position. We need to talk about motion, so we need to talk about how they are moving. While water particles are moving throughout the liquid. State the name of the thermal process that transfers energy from water to ice. This is known as conduction. Initially, there is 0.34 kilogram of water in the beaker. The specific heat capacity of water is 4,200 joules. Calculate the energy transferred from this water as the temperature decreases from 28 to 10 kg. Now we know the formula. Q equals mc delta theta. Mass is 0.34. Specific heat capacity is, I like to write my units, kg times 4200 joules multiplied by delta theta, which is the change in temperature. 28 minus 10, 2.6 times 10 power 4 joules energy transferred. The temperature of water near the ice decreases first. Explain how convection causes the temperature of all the water in the beaker to decrease. So convection is basically the flow of heat, right? Hot water particles rises, the cool, denser particles settle down. Temperature of water near the ice decreases first. So when low temperature, small temperature, more density, so it sinks. Basically, that's the idea. So they're saying that the temperature of water near the ice decreases first. That means low temperature particles near ice, they have increased density. So this cold water sinks to the bottom. The warm water, now this is heavy cold particles, so they're going down now, and this warm water is going to go up. Warm water replaces cold water at the top. State what happens to the internal energy of the water as the temperature of the water decreases. Describe the change in terms of energy of the particle. What happens to internal energy as the temperature is decreasing? Internal energy also decreases. And since it's becoming solid, the particles are going to vibrate less, and with less kinetic energy. They have more temperature, they're moving more. Average kinetic energy, make sure to write full word. Kinetic energy decreases. A lens in a magnifying glass is a converging lens. Its two focal points f1 and f2 are on its principal axis. This line is called the principal axis, and these 2 points are focal points. What is a focal point? Focal point is point on principal axis where rays of parallel light converge. This means that, for example, if the in this image, if the light is moving parallel, we can draw a lens like this. This light ray is moving parallel, another light ray is moving parallel. This is going to converge at this point. This light is going to converge at this point. You get our focal point. Student uses a magnifying glass, sees a magnified object image on the object. On figure 4.1, mark the point X on the principal axis for the possible of the object. Position E for the possible position for student's eye. So first we need to find what is the position of the object. This is our object and this is our object. We can label it X. And the eye is here. This is point E. Underline two words in the list that describes the image produced. First of all, this is an upright image and it is a virtual image. Magnifying image is upright and virtual is not a real image. The refractive index of the glass used to make the lens is 1.5. The speed of light in air is 3 times 10 power 8. Calculate the speed of light in the glass. N equals C over V. Speed of light in the glass. So velocity is going to be 3 times 10 power 8. Speed of light in air divided by 1.5. This is going to be, don't forget the units again. State what happens to the wavelength of light as it passes into the length. You know that V equals F lambda. As long as the frequency is same, velocity and lambda are directly proportional. Velocity is reducing, so wavelength is also reducing. Whenever you see the word state, they just want a word, they don't want an explanation. State means one word. Converging lenses are used in spectacles to correct one problem with vision. State the name of the problem and explain how a converging lens is used to correct it. You may draw a diagram. So this is called as long-sightedness. That means people can see from far, but they cannot see images close to them. Let's draw it in case when the people are long-sighted people. And this is, let's say these are their eyes. What happens is that instead of forming on the retina, the image forms outside the retina. This is the image. So what our lens does is that let's say this is our eyes, this is our lens, and this is our retina. It converges the image before, so the image can form on the retina. This is the image, right? So what we can say is it moves the image this problem moves the image outside the retina, which is back of the eye, and the lens on the retina. How longitudinal wave differs from transverse wave. So in longitudinal, the particles are vibrating parallel to the propagation direction. Direction of propagation is basically where the wave is heading towards. Propagation. And in transverse, particles are vibrating perpendicular. If you want another easier one, you could say that longitudinal needs a medium to travel. For example, sound wave. Sound wave cannot travel in vacuum. Transverse doesn't need. It can travel in vacuum. For example, light waves. All the electromagnetic waves are transverse waves. Now, figure 5.1 represents a seismic wave produced by an earthquake. State whether this wave is P wave or S wave. This is a P wave. Why? Because it's a longitudinal wave. Now, the wave represented on figure 5.1 has a wavelength of 1.2. Calculate the actual distance between J and K. Now, wavelength is distance between two compressions or rarefactions. So if you see here, from point J, we need to find the actual distance between point J and point K. First, let's try to identify our wavelength. So this is one compression, this is another compression. So all this is one wavelength. Now from here to here, this is another wavelength, but we need to find midway. So this is going to be half of wavelength. So in total, what we have is 1 plus 1.5. We have 1.5 of our wavelength. Now if one wavelength has 1.2 times 10 power 4 meter of distance, so what about 1.5? When the wavelength is 1.5, what is it going to be? The distance is going to be 1.5 times 1.2 times 10 power 4 meters. 1.8 times 10 power 4. The wave in truth travels through the ground at a speed of 4,600 meters per second. As the wave passes a certain point, the ground completes 5 oscillations. Calculate the time it takes for the wave to pass. So we know that frequency is 1 by time period, and v equals f lambda. We need to find the time taken for the wave to pass. We need to find time. We have velocity, we have wavelength. Now v equals lambda divided by time period. Time period is going to be wavelength, which is 1.2 times 10 power 4 divided by velocity, which is going to be 4600, 2.6086 seconds. Now this is the time taken to pass for one oscillation. To calculate the time taken for 5 oscillations, we have to multiply the time period by 5. We get 13 seconds. Figure 6 shows an isolated metal sphere suspended by an insulating thread from the ceiling. The sphere is negatively charged. The charge on the sphere produces an electric field in the surrounding. Negatively charged. What is meant by an electric field? It is a region where an electric charge experiences a force. Means is that, for example, it means that there is an electric field. This is the electric field. If I keep a charge here, it's going to either get attracted or repelled. It is going to feel a force. Outside the electric field is not going to experience any force, no attraction, no repulsion. So this is what an electric field is. It's the region of space. On figure 6.1, draw the pattern and direction of the electric field produced by the charge in the sphere. On the sphere, draw at least 4 lines. This is inwards, right? So try to draw 4 lines. Make sure that the forces are around equally spaced. Like that. You don't have to measure it, but it should approximately close to each other. Use a ruler and draw properly. This is negative and positive sphere. It was going outwards. Okay, the magnitude of the charge in the sphere is 3.5 times 10 power negative 10 coulombs. An earth metal wire is touched against the surface of the sphere and the sphere is discharged. State what happens in the wire as the sphere is discharged. So if there is an electric wire that's connected to this electric wire, don't draw it here, but I'm just explaining it. The electrons are going to move through the wire from the sphere, right? Electrons are going to move out like this. Let me erase this. The electrons move through the wire from the sphere. It takes 0.14 nanoseconds for the sphere to discharge completely. Calculate the average current. Now we know Q equals IT, I equals Q over T, which would be 3.5 times 10 power negative 10 divided 0.14 times 10 power negative 9. The answer is 2.5. The electromotive force of a battery 7.5. Describe the term electromotive force. Basically, it's the work done to move a charge a unit charge around a complete circuit. Let me try to explain it in a drawing. You don't have to draw it, but it's just for explanation. For example, this is our battery, and the electrons are going to move from this point, and they're going to move all the way back to this point. Now, the work done to move our charge from here around the complete circuit back here is known as electromotive force, or EMF. This is also the one EMF or voltage. A battery is connected in series with a variable resistor and a 30 ohm resistor. The battery is made using 1.5 volt cells. Draw circuit diagrams to show how all 1.5 volt cells connected to produce an EMF of 7.5 variable resistor and a 30 ohm resistor. So to get 7.5, we'll need 5 1.5 volt cells. So let's connect them in series, positive and negative. 2, 3, 4, 5, connected to a 30 ohm resistor. And a variable resistor. Make sure to draw the correct symbol. The resistance of the variable resistor can be varied from 0 ohms to a maximum resistance of 150 ohms from 0 to 150. Use the axis, draw a graph to show how the current in the circuit varies with the resistance of the variable resistor as it increases from 0 to 150. Now the relationship between current and resistance is that they are inversely proportional. I is inversely proportional to resistance. Now we need to determine and label the value of maximum current on the y-axis. I equals V by R. Here, what is the voltage is 7.5. That is the maximum voltage. And to get the maximum current, we need to use minimum resistance. Now, minimum resistance, if it's 0 of the variable resistor, we still have 30 ohms. So it's 30. Let's say this one is 0 ohms. 30 and 0, that's when we'll get maximum current. So we have to use 30. 7.5 divided by 30, we get 0.25 amps. So this is 0.25. Moving on, the isotope thallium 208 is radioactive. It decays by beta decay. Thallium decays to an isotope of lead. Now we don't have a periodic table. We need to do our calculation here. Now the beta is 0 and -1, right? So this remains same, 208, but here we get -1, so this is supposed to increase. Let's see our calculation. 81 equals to 82 plus -1, that's correct. 208 equals 208 plus 0. The beta emission of thallium is accompanied by gamma emission from the nucleus. Explain why this emission does not affect the numbers in equation A1. You can see that 208 remains 208 because gamma emission is basically a wave. Gamma consists of waves. It has no mass, so it cannot affect the mass of lead. Mass or even charge. No mass, no charge, doesn't affect. Just one reason why nucleus of thallium 208 is unstable. It has a lot because the nucleus is too heavy. It has a lot of neutrons. A lot of neutrons can make our atom unstable, our element unstable. A sample of thallium is placed in a thick lead container. Figure 8 shows a narrow beam. This narrow beam of beta and gamma particles emerging from a small hole in one side of the container. The narrow beam enters a region where there is a magnetic field that is directed into the page. Draw a line labeled beta to indicate the path of beta particles, and draw a line gamma. So let's draw gamma first. Gamma has no charge, no particles, so it's just going to go straight. We will label this gamma. So to draw the beta particles, we have to use Fleming's left-hand rule. As we know that here they have mentioned that the magnetic field is directed into the page, so current is going down. This is negative and this is positive. We know beta particles are negatively charged, so they're going to be deflected and attracted towards the positive side. The sun is one of many billions of stars in the Milky Way. The sun emits a very large quantity of energy as electromagnetic radiation. State 3 regions of electromagnetic radiation in which the sun emits the most energy. First of all, of course, visible light. We get all our light from sun. Second of all, ultraviolet and infrared. Electromagnetic radiation from the sun travels at a speed of 3 times 10 power 8 meters per second. The radiation takes 500 seconds to reach the earth. Calculate the distance from sun to earth. We have to use a basic speed time equation. Velocity equals displacement over time, which is speed is distance over time. Distance is going to be 3 times 10 power 8 multiplied by 500. this is very basic, 1.5 times 10 power 11 meters. Approximately 4.6 billion years ago, the sun formed an interstellar cloud of gas and became a stable star. Describe and explain what happens as an interstellar cloud of gas forms a protostar. As there is a transition from interstellar cloud of gas to a protostar, what happens is that there is a high gravitational attraction and what this does is that this causing the cloud to collapse. And the internal temperature rises. Describe and explain what happens as this protostar now becomes a stable star. So we know that the temperature is high. Because of the high temperature, a nuclear fusion happens inside one star. There's a nuclear fusion and high temperature. There will be an outside force which balances the inward gravitational force. That's it. And we are done.